Swayam Prabha. Digital India. Educated India.
In the previous lecture, we saw how the law of the wall for velocity, that is for u plus, can be used to evaluate friction coefficient Cfx for both external boundary layers as well as for pipe flows, irrespective of the pressure gradient and also the effect of surface velocity Bw or the surface roughness. In all those cases, we were able to obtain coefficient of friction as a function of the Reynolds number, the local value of Reynolds number. Today, we are going to look at how the temperature law of the wall can be used to predict the Stanton number in external boundary layers and Nusselt number in internal flows. Again, most of these methods are essentially analogy methods, that is a similarity between heat transfer and momentum transfer is one way or the other assumed, and we would be able to predict the variations of Stanton number and Nusselt number as functions of Reynolds number as well as Prandtl number. So, I would first deal with external boundary layers in 4 different ways. One is use of the law of the wall for situations in which there is no suction or blowing. I would also use analogy methods. Then I will show you how to apply integral method, that is the solution of the integral energy equation, to take care of effects of pressure gradients, wall temperature variations. And then finally, we will extend the method to take care of the effects of roughness and suction and blowing. Likewise, we will look at prediction of Nusselt number in pipe flows, internal flows, and again make use of the law of the wall as well as the analogy methods. So, let us start with the external boundary layer case, and from lecture 28 you will recall that the temperature law of the wall is written as T plus equal to Prandtl u plus plus Pf, which is a function of u plus. But if we write that equation in the infinity state, we would get T infinity plus equal to Prandtl T into u infinity plus Pf infinity, which as you recall is a function of Prandtl number only. So, u infinity plus here would be simply u infinity by u tau, which is u infinity under root tau wall by rho, or it can be written as under root rho u infinity squared divided by tau wall, which is nothing but under root 2 by Cfx. T infinity plus, as you will recall, is defined as minus T infinity minus T wall divided by q wall by rho Cp u tau. So, if I divide and multiply this by in u infinity and note that q wall divided by T wall minus T infinity is Hx, the heat transfer coefficient, then you can see that this part is the Stanton number, 1 over Stanton number, and u tau or u infinity is nothing but under root Cfx by 2. And as a result, this equation simply transforms to Stanton x equal to Cfx by 2 square root into Prandtl T into under root 2 by Cfx plus Pf infinity. And as you will recall, I said the turbulent Prandtl number is approximately 0.9, some people take it 0.85, but that is still, one can make Prandtl T also a function of Prandtl number itself, as I indicated what the possible correlation could be. For Prandtl number 1, you recall Pf infinity is 0, so that is 0 for Prandtl number equal to 1, and Reynolds actually used Prandtl T equal to 1, and hence then you will see the Stanton X would simply be CFX by 2, which implies perfect analogy between heat transfer and momentum transfer. From experiments for near unity Prandtl numbers, Stanton X correlates as CFX by 2 into Prandtl raised to 0.4 minus 0.4, and hence for 0 pressure gradient boundary layer, Stanton X is equal to 0.0286 Reynolds X to the power of minus 0.2, Prandtl to the power of minus 0.1. This was the correlation you use routinely in your undergraduate work, and we have shown that it can be derived from this equation, the temperature law of the wall. Of course, if you had a rough surface, then one must evaluate CFX for a rough surface, and PF infinity also must be used for a rough surface, so as to get Stanton number for a rough surface. Now, in all this evaluation, you can see that CFX must be evaluated from the methods of the previous lecture. So, whatever the pressure gradient or VW or whatever is present, you simply use that to evaluate CFX, and straight away evaluate Stanton X from that. This is the simplest way to evaluate Stanton number, but then we can also apply somewhat more rigorously analogy method, in which we call that the effective Prandtl number is essentially dt plus by du plus, which we can write as dt plus by dy plus multiplied by du plus by dy plus. Then this should be raised to dy plus by du plus, it should be not du plus by dy plus by du plus, and hence using the relation tau tot divided by tau wall is approximately equal to 1 plus nu t by nu du plus by dy plus. You will recall we had derived this equation, gives dt plus by dy plus equal to 1 plus nu t by nu du plus by dy plus Prandtl raised to minus 1 plus nu t by nu into Prandtl t, or simply 1 over Prandtl number into 1 over du plus by dy plus minus 1 over Prandtl t raised to minus 1. Integrating from y equal to 0 to infinity and using the 3-layer law for u plus, and hence for du plus by dy plus, it follows that. Now, if I pollute du plus by dy plus for the laminar sublayer is equal to 1, then of course that quantity vanishes, and I simply get T edge of the sublayer plus minus 0 equal to Prandtl y SL plus equal to Prandtl u SL plus, and as you know, u SL plus and y SL plus are 5. So, therefore, you get T SL plus is equal to 5 Prandtl. Extend the integration further from sublayer to transitional layer. So, T transitional layer plus minus TSL plus, and here du plus by dy plus would become 1 over kappa y plus, where kappa is 0.2, and therefore, that will become 5. So, 5 Prandtl t ln 1 plus 5 Prandtl by Prandtl t, and here I have used transitional layer as y plus for transitional layer as 30, then you get that relationship, and then from the edge of the transitional layer till the edge of the boundary layer, you will get T infinity plus minus T transitional layer plus, again du plus by dy plus will be 1 over kappa y plus, and therefore, where kappa is 0.4, then you will get that relationship, that involving delta plus the boundary layer thickness. So, we got essentially layer by layer contributions to T infinity plus. And if I add these 3 equations, as I show on the next slide, and rearrange, if I add these things, then you will see T SL plus here gets cancelled with that, this gets cancelled with that, and I would get a relationship for T infinity plus, which, as you will recall from the previous slide, T infinity plus is nothing but CFX by 2 by Stanton. Then I get CFX by 2 divided by Stanton X equal to 5 Prandtl plus all this. This is the transitional layer contribution, this is the laminar sublayer contribution, and this is the fully turbulent layer contribution. Now, how do we evaluate delta plus here? Well, as you will recall, in the outer layers, delta power law very well applies. So, instead of logarithmic law, if we apply power law, then simply delta plus is equal to u infinity plus divided by 8.75 raised to 7, or that is equal to this quantity. The CFX is evaluated by integral methods of equation of lecture 29. So, you substitute delta plus here as CFX, and CFX that appears here and here are both first evaluated from lecture 29 for a given situation, and that gives you the variation of Stanton number as a function of Reynolds number and Prandtl number. Now, when u infinity and Tw minus T infinity vary arbitrarily with x, then one must invoke the integral energy equation, which reads as 1 over u infinity into Tw minus T infinity d by dx delta 2 u infinity Tw minus T infinity equal to Stanton x. So, you recall this integral energy equation when Vw is 0. Now, for further analysis, let Stanton x be equal to C Reynolds x to the power of minus n. Now, this method is often called the Ambroch's methods. Ambroch was a Soviet scientist and he published a paper on this. So, for the moment we will simply assume that the Stanton x will vary as C times Reynolds x to the power of minus n, and that is substituted here. Then for u constant u infinity and Tw minus T infinity boundary layer, that is let us say fat plate, it will simply mean d delta 2 by dx equal to Stanton x equal to C u infinity x by nu raised to minus n, and if we integrate that, I will get delta 2 equal to C over 1 minus n u infinity by nu raised to minus n x raised to 1 minus n. And if I use the idea that delta 2 is 0 at x equal to 0, that is right at the leading edge, then Stanton x would simply become that. Stanton x would simply be function of delta 2 raised to n over n minus 1. Now, this is a very important relationship because we will be subsequently using this relationship for a variety of situations. So, we assume the validity of the last relationship regardless of the previous history of the boundary layer. Then the integral energy equation becomes d delta 2 u infinity Tw minus T infinity of d by dx, and then that is equal to u infinity Tw minus T infinity C 1 minus n by C u infinity delta 2 by nu n over n minus 1. And if we were to integrate this equation, you will get C nu raised to n 1 minus n u infinity Tw minus T infinity 0 to x u infinity Tw minus T infinity 1 over that. So, in effect then I can calculate delta 2 for any arbitrary variation of u infinity and Tw minus T infinity with respect to x. If I use now the previous Stanton x delta 2 relationship of this type, then you can see I can get Stanton x equal to C nu n Tw minus T infinity raised to n over n minus 1 divided by this integral, and this essentially allows you to calculate Stanton x for any arbitrary variation of free stream velocity and wall temperature. Now, assuming the flat plate data for C equal to 0.0284 Prandtl raised to minus 0.4 and n equal to 2, you will recall I showed this to be the case in the first slide here, that Stanton x can actually written as 0.0286 Reynolds x to the power of essentially if I say C is equal to 0.0286 Prandtl raised to minus 0.4 and n equal to 0.2, then that is what I have done here. I would get a relationship for Stanton x equal to this quantity, and you will recall that uw is u infinity is actually the pressure gradient. Although these constants are strictly valid only for flat plate, but this Stanton number expression has used the same value of C and n, and you get this relationship for Stanton x. Now, Crawford and Case have actually experimented with the constant wall temperature boundary layers in which the free stream varies arbitrarily. That means only free stream varies arbitrarily, not Tw minus T infinity, and their experimental data fit this correlation very well. This is the pressure gradient parameter nu infinity square du infinity by dx is the pressure gradient parameter less than 10 raised to plus 6, and the Stanton number evaluated from this relation, this integration, and that evaluated from this agrees extremely well, and therefore we can say that use of C and N in this manner appears to be quite valid even for situations in which U infinity is not constant or TW is not constant. So, with this experience, we now move forward and look at situations in which there is suction and blowing. So, now again, for a flat plate and TW minus T infinity constant, Crawford and Craig show that for finite VW, Stanton x when VW is finite is equal to divided by Stanton x when VW equal to 0 can be written as ln 1 plus BH by BH, and BH is nothing but our blowing parameter, but this time based on Stanton x. We shall derive this relationship later on when we consider mass transfer problem, in which the suction and blowing would be viewed as a problem of mass transfer, and the BH then is defined in this fashion. And Stanton x VW then, and substituting for Stanton VW equal to 0, which is 0.0284 Prandtl point minus 4 Reynolds x to the power become into ln 1 plus BH by BH. That is what becomes. And the energy equation with for a flat plate where U infinity is constant and TW minus T infinity equal constant, will energy equation would simply be d delta 2 by dx Stanton x VW plus VW by U infinity. But if I substitute this for Stanton x VW, if I substitute for VW by U infinity is equal to BH into Stanton x VW, then you will see it simply becomes that 1 plus BH, or the total expression then can be written in this fashion, Reynolds x to the power of minus 1. So, there is ln 1 plus BH multiplied by 1 plus BH divided by BH, Reynolds x to the power of minus 0.2. If BH was constant, then the entire term here on the inside the bracket would be constant, and it is not very difficult to integrate this equation using delta 2 equal to 0, x equal to 0. Gives the integration gives Re x to the power of minus 0.2 equal to this relationship multiplied by Re delta 2 raised to minus 0.25, or using again the Stanton x Reynolds Re x relationship of the previous slide here, the solution can be written as Stanton x for a finite VW is written as 0.0125 Prandtl raised to minus 0.5, Reynolds delta 2 raised to minus 0.25, 1 plus BH raised to 0.25, and then this factor raised to 1.25. Of course, this integration was made possible by assuming BH equal to constant. Now, like in the previous case, we shall assume the validity of this relationship between Stanton x and delta 2 even when BH U infinity and TW minus T infinity vary arbitrarily with x. So, that is what I have done next slide. So, for this case, then the integral energy equation will read like this into all this quantity into that, and then if we were to integrate as in the previous case, you get Stanton x will be equal to 0.0284 Prandtl raised to minus 0.4, then BH now varies with x. So, that is included, and you can see I can perform this integration for any arbitrary variation of U infinity, TW minus T infinity and BH, so that I can get variation of Stanton x. Crawford and Case have show remarkably good fit to experimental data and predictions using mixing length. So, they had a situation in which a highly accelerated boundary layer was considered with VW present and it was changing arbitrarily. And therefore, the problem was solved by a mixing length model and predictions were obtained. Experimental data were available for the same case, and then this expression, this approximate expression derived from Ambrox's procedure was used, and very good agreement was shown between experimental data and the correlation as well as predictions using mixing length. With this, I end the methods in which law of the wall is used or integral energy equation is used. And now I turn to the differential equation based methods, which are, and it so happens that you can use similarity type methods for turbulent boundary layers as well. And the governing equation for the temperature boundary layer would read as u dt by dx v dt dy plus nu times, equal to plus nu d by dy b Prandtl dt by dy, where b Prandtl is alpha by nu and alpha t by nu, which is Prandtl raised to minus 1 plus Prandtl t raised to minus 1 into nu t plus. And nu t plus, as you will remember, is nothing but nu t by nu, and nu t would be given by Prandtl's mixing length as a function of y, the distance from the wall. In lecture 29, I introduced the similarity variables to be used for turbulent boundary layers, and if we use the same similarity variables, then the equation for turbulent heat transfer boundary layer would be given by this: d by d eta into b Prandtl into theta prime plus f theta prime plus 2n over m plus 1 f dash 1 minus theta equal to again a function of x on the right hand side. This was also found in case of momentum equation, that you do get things on the right hand side which are functions of x, where the things on the left hand side are essentially functions of eta. So, here m is the pressure gradient parameter defined as x over u infinity du infinity by dx. N is the parameter related to wall temperature variation. So, n would be 0 of course if Tw was constant, and theta is defined as Tw minus T over Tw minus T infinity. And again, like in the velocity boundary layer case, you need to, of course, f dash are available already from the velocity boundary layer solutions, and therefore, solutions for theta would be obtained by iterative method, just in the manner in which the similarity solution for velocity was solved. The boundary conditions are, of course, theta equal to 0 at eta equal to 0 and theta equal to infinity would be equal to 1. That completes discussion of the external boundary layers and the similarity method. You need to do is at every x you solve the left hand side by shooting method. The right hand side is evaluated from values available at the one step before it, so that the right hand side can be formulated as a constant for that step. And one simply solves the left hand side again by shooting method. Using the intermediate solution for theta, the right hand side is evaluated again and till convergence is obtained, and we accept the solution at that position x and move to the next step. I now move to internal flows. So, we wish to use the wall law for pipe flow. So, if I write the T plus equal to u Prandtl T into u plus plus Pf infinity corresponding to central line, then TCl plus will be that, and UCl plus you will recall is nothing but u bar plus 1.5 by kappa plus Pf infinity. So, where TCl plus now would get defined in this manner, Tw minus, actually it will get defined as Tw minus TCl divided by Qw, but if I multiply and divide by Tw minus T bulk, then you will see this gets Tw minus T bulk over Q wall, Tw minus TCl over Tw minus T bulk multiplied by rho Cp and U tau. That would be the definition of TCl plus. Now, I multiply by K and divide by K, I multiply by U bar and divide by U bar, then you will see this can be written as, this is nothing but 1 over h, the heat transfer coefficient, into K divided by diameter, which I have divided by and now again multiplied by. So, I get U bar d by alpha multiplied by U tau over U bar multiplied by T wall minus TCl divided by T wall minus T bulk. Now, K over h d is nothing but 1 over Nusselt number, U bar d by alpha is nothing but Peclet number or product of Reynolds number and Prandtl number. So, these two factors are nothing but Reynolds Prandtl divided by Nusselt number. U tau over U bar would be simply under root f by 2, the friction factor for a pipe flow, multiplied by T wall minus TCl divided by T wall minus T bulk, and hence equating TCl plus from this expression and from this expression, that is the law of the wall, then you will see I can write Nusselt number equal to Reynolds Prandtl under root f by 2 divided by Prandtl T into under root 2 by f plus 1.5 kappa plus Pf infinity, and this becomes Tw minus Tcl over Tw minus T bulk. To use this relationship, we would of course need estimate of Tw minus T center line divided by Tw minus T bulk, which we expect to be somewhat greater than 1 in a turbulent pipe flow, because remember the temperature profiles are very flat inside the core of the flow, and there are sharp gradients of temperature near the wall, and therefore the ratio of Tw minus Tcl divided by Tw minus T bulk would be only slightly greater than 1. So that is what we shall show. Now, many times, quite analogous to what is power law for velocity, you assume a validity of the power law even for temperature, T minus Tw divided by T center line minus Tw equal to y by r raised to 1 by 7, and which we said would be equal to u over uCl. Then using definition of T bulk, as you know, which is simply integral 0 to r ut r dr divided by integral u r dr. It is easy to show that Tw minus T center line divided by Tw minus T bulk would be about 6 by 5, which is close to 1, let us say, or 1.2, 1 to 1.2. Remember, this relationship is not absolutely exact, but we can take it to be between 1 and 1. It is a function of Reynolds number. You will notice that for high Reynolds number, you need to take this as 1 over 9, whereas below 50,000, it can be taken as 1 over 7. So, as a result, Tw minus Tcl over Tw minus T bulk is actually a function of Reynolds number. This factor turns out to be function of Reynolds number. The higher the Reynolds number, closer it gets to the value of 1. And likewise, uCl by u bar is 1.22, but that's too high an estimate, but nonetheless can be taken to be approximately so, close to 1. Then you can substitute these values for uCl by u bar, and I mean mainly you want this value, but that the evaluation of that value requires this value, so that's why I have quoted it. The most widely used correlation for pipe flow, which is considered to be very accurate with experimental data, is the one by Gnian-Lenski, and it reads like this: Nu equal to Reynolds minus 1000 Prandtl under root f by 2 into 2 by f plus 12.7 Prandtl raised to 2 by 3 minus 1, and it is valid for gases to heavy oils 0.5 to 2000 and 2300 to 5 million Reynolds number. So, notice the similarity between the equation we have derived here. So, instead of Reynolds, the Gnian-Lenski correlation has Reynolds minus 1000. Prandtl number is still there, under root f by 2 is very much there. Prandtl T is perhaps taken as 1, and then there is a factor of 2 by f, and then there is, remember this is 3.66 in our calculation, and then the Pf infinity, which we use from our correlation. But Gnian-Lenski takes Prandtl T equal to 1. He is also taking the ratio, if you like, of this to be nearly 1, and then this is the function of the Prandtl number. So, this most widely accepted correlation has a form which is very similar to what we derived from the temperature law. We can also apply analogy method for pipe flow. So, for fully developed pipe flow, for example, dP dx is equal to constant. Hence, the axial momentum equation and its consequences are that 1 over r dr tau taught by dr would be equal to minus dP by dx, and integration would give tau taught by tau wall equal to r by r, meaning the total stress divided by the wall stress is a linear function of r by r, and this we had shown from the experimental data in an earlier slide. and replacing r equal to r minus y, the capital radius minus y, as a distance from the wall, it will be 1 minus y over r. So, tau tot is equal to rho times nu t du dr, and that would become minus rho nu plus nu t du by dy, and therefore 1 plus nu t by nu can be shown to be 1 minus y plus by r plus divided by du plus by dy plus. So, that is what I shall use to substitute in our, from slide 2 here, I would use that to substitute for du plus by dy plus and nu t by nu. Sorry, I would use that to do this 1 over nu t by nu. Then you will see that dt plus by dy plus now is 1 minus y plus by r plus over 1 over Prandtl number 1 minus y plus by r plus over du plus by dy plus minus 1 over 1 plus 1 over Prandtl t raised to minus 1. And now we will evaluate du plus by dy plus for each of the 3 layers, that is sublayer, the transitional layer and the fully turbulent layer, and this is what the integration gives you for 3-layer law. TSL plus minus 0 equal to that as before. This is also everything is as before for an external boundary layer, and the TCL plus minus T transitional layer would give you 2.5 Prandtl T ln r plus by 30, again for Prandtl greater than or equal to 1, but also gases can be included, which is very close to 1. So, if I add these 3, I would get TSL plus, before adding of course, TCL plus by definition is Reynolds Prandtl over Nu over this we showed on the previous slide. If I equate this equal to the summation of the 3, I would get the expression for the Nusselt number, where r plus is now expressed as Re by 2 under root f by 2, and therefore Nusselt number would become Re Prandtl f by 2 T wall minus TCL T wall minus T bulk divided by the entire quantity here, and this will be the second expression we have got now for representing Nusselt number. Now, of course, you have been using quite routinely the Dittus-Boelter correlation for very simple as Nu equal to 0.023 Re raised to 0.8 and Prandtl raised to n, where n is equal to 0.4 for heating case and n equal to 3 for cooling case. In chemical engineering literature, most often the correlation due to Schleicher and Rouse is used, and it says Nusselt number is equal to 5 plus 0.015 Reynolds raised to A and Prandtl raised to B, and this is valid for 0.1 to 10,000 and Reynolds number from 10,000 to a million, and A is made a function of Prandtl number and B is made again a function of Prandtl number. So, these are some of the experimental correlations which are routinely used. Now, as I said, all this in our analysis is actually for Prandtl number greater than 1, but for liquid metals, Nusselt number is correlated in this fashion: A plus B Re raised to 0.85, Prandtl raised to 0.93, and where A and B take these values. Now, remember I said in my lectures when I introduced turbulent flow that Nusselt numbers do not respond to the boundary conditions like in laminar flow. Nusselt numbers in turbulent flow are relatively insensitive to whether it is a constant wall heat flux boundary condition or constant wall temperature. But that argument applies only to gases and situations in which Prandtl number is greater than 1. When you come to liquid metals, they develop character. The thermal boundary layer thickness now enters the transitional layer and also inner part of the turbulent layer many times, depends on the value of Prandtl number. And in such situations, the boundary condition begins to influence events even in turbulent flow. And that is what is shown here, that the constants A and B should be modified as shown here for Q wall equal to constant and T wall equal to constant. So, what it shows is again the heat Nusselt number for constant wall heat flux will be greater than the Nusselt number for constant wall temperature, a circumstance very similar to that found in laminar flows. By taking temperature ratio as 1.1 and Prandtl T equal to 0.943887, and you recall I had given you the relationship that Prandtl T actually can be modeled as Prandtl T equal to 0.85 plus 0.0309 into Prandtl divided by Prandtl plus 1. Sorry, this should be Prandtl 1 divided by Prandtl. Then you will see that this relationship assumes for Prandtl greater than or equal to 1 will give you, for example, at Prandtl equal to 1, this will simply make it about 0.06, and Prandtl T will be about 0.91 for Prandtl equal to 1. And for very large Prandtl numbers, also it will be around 0.88, because this ratio would be 1. But now imagine for liquid metals where Prandtl number is, let us say, of the order of 0.001, then you will see this quantity becomes 1.01 divided by 0.001, or nearly 1000, and therefore this will become almost equal to 31.0. So Prandtl T can be very large for a very small Prandtl number, that is liquid metal. But I am presently considering cases in which only, say, from gases to organic liquids, so Prandtl 0.5 to 5 and 25, and I have calculated Prandtl T using the relationship that I just showed. So it is 0.943 here for 0.5, Prandtl T equals 0.87 for Prandtl equal to 5, and 0.82 for Prandtl equal to 25. And the temperature ratio I have always taken as 1.1 in each of those cases. Then just see what happens. So at Reynolds number 3000, Ginelensky correlation predicts 8.13, whereas Ditters-Boelter predicts 10.5. Schleicher and Rouse produce 11.9, whereas the analogy method produces 10.3. And similarly at 10,000 and 50,000 and 1 lakh and 1 million, then you will see that Ginelensky and other correlation predict very well, are comparable, Nusselt number, but Ditters-Boelter is way out, as you can see. For high Reynolds numbers, Ditters-Boelter relationship predicts much higher than predicted by any of the other correlations for gases. What about water? Something very similar. You will see that that at sufficiently high Reynolds numbers, say 10th, these correlations are close to each other. But again, at higher Reynolds number, Ditters-Boelter under predicts the Nusselt number compared to other correlations, whereas for gases it was over predicting, for water it is under predicting, and that trend continues even for organic liquids. So for Prandtl greater than 1, apparently Ditters-Boelter under predicts, whereas for Prandtl less than 1, it over predicts compared to the correlations that are well accepted. Ginelensky in particular is very well accepted correlation. So from these relative comparisons, we say that the correlations for pipe flow can be applied to, of course, non-circular ducts by evaluating F, Reynolds and Nusselt number based on hydraulic diameter. This you have routinely done in your undergraduate work. Of course, the theory to support this assumption requires solution of Reynolds stress equations, so that the secondary flows predicted in the cross section by the Reynolds stress model can actually explain why hydraulic diameter concept works for non-circular ducts. The easy to use Ditters-Boelter correlation, although it is very easy to use, actually over predicts Nusselt number for Prandtl greater than 1 and under predicts for Prandtl greater than 1. For a complete description of flow and heat transfer involving complex ducts, strong and changing strain rates due to body forces, and it is best to use CFD techniques with 2 equation or stress equation models. This completes our discussion on turbulent flow and heat transfer, and henceforth now I will begin with convective mass transfer.